Hello, I'm Michael Wunsch. I'm the plant pathologist at the North Dakota State University Carrington Research Extension Center. I'd like to take a moment to share with you what we have learned about optimizing fungicide droplet size relative to canopy characteristics for improved white mold management in pinto beans. We started this research on the basis of what we learned in soybeans, where we found that we could drastically and very sharply improve fungicide performance against white mold by calibrating fungicide droplet size relative to canopy closure. Fine droplets were only optimal for managing white mold in soybeans when the canopy was wide open. And as that canopy got denser, we had to use progressively coarser droplets. So naturally, we wanted to know whether we'd see something similar in dry beans. As a bit of background, when you see a droplet size, remember that that droplet size refers to the diameter of the droplet. And when you cut that droplet size in half, you're actually dealing with volumes and you get 8 droplets rather than the 1. And when you cut that droplet size in half again, you get another 8 droplets from each of those initial 8 droplets, i.e. 64 droplets. So what does this mean in terms of fungicide activity? Remember that fungicides only move, the modern fungicides only move in a locally systemic manner upward with the water conducting cells of the plant from the point of deposition. And they only move a limited distance upward. So on that top leaf that received a singular 500 micron droplets, that fungicide, if you're lucky, will move from that point of deposition to the top of the leaf, but it may not even move that far. But in the best case scenario, it's going to move from that point of deposition to the top of the leaf, and that leaves the bottom third of the leaf unprotected with no fungicide. So now if we cut that droplet size in half, and we get 8 droplets and we spray that into the canopy and all 8 droplets fall on that leaf, i.e. the same volume of fungicide on that leaf. Notice now the odds that that fungicide is distributed across the leaf are much better. You have 8 droplets, and if they're distributed the way it's shown in this picture, what you can see is that with that local systemic movement upward from the point of deposition, you're going to be protecting at least 90% of the leaf rather than, say, only 2/3 of the leaf. So that's much better. That's why we want coverage. Now, what if we cut that droplet size in half again, and now suddenly we have 64 droplets? If we're able to get those droplets to that leaf and that exact same volume of fungicide lands on that leaf, now suddenly we have the whole thing protected. And it's because of this local systemic movement, the fact that the fungicides do not move downward from the point of deposition, that you always hear this mantra, you want coverage with fungicides. You want to spray with fine droplets. But there is a problem with fine droplets because fine droplets do not have the velocity to penetrate a closed canopy. And when you have a disease that's developing in the interior of that canopy, you need to get inside that canopy. So what do I mean by that? This graph on the left shows the droplet size diameter versus the velocity of those droplets. The pink bar shows those droplets emitted at 58 psi. The dark blue is 44 psi, and the light blue is 29 psi. And what you'll notice is that those fine droplets, even when they're shot out at 58 psi, they do not have very much velocity. You need to get a coarser droplet that weighs more to be able to get some velocity. And when you have that greater velocity, you also get less drift. Okay, when you have that greater mass, okay, you get less drift. And when you have less drift, it's a lot easier to get your product to your target. So, how do we do this research? We used TJet nozzles simply because they have wide market acceptance in North Dakota and Minnesota. All the growers and crop advisors know them. We used TJet extended range flat fan nozzles because it worked for our driving speeds and spray volumes. We selected nozzles and application pressures on the basis of the charts in the TJet catalog, and then we double checked the actual droplet size spectrum produced by asking Winfield United to characterize the droplet size spectrum with their laser-based system in their wind tunnel in their R&D facility in River Falls, Wisconsin. What we found is that the nozzles and pressure combinations that we utilized to apply fine droplets applied droplets right at the boundary of fine and medium. So one of them applied droplets in the fine spectrum, but just barely within the fine spectrum. Usually the cutoff is 250, a DV50 of 250 microns. What this means is the droplet size diameter of 250 microns represents the diameter whereby half of the spray volume is deposited with droplets smaller than that, and half of the spray volume is deposited with droplets larger than that. Okay, so at any rate, with our fine droplet treatments, we ended up with treatments that were right on the boundary between fine and medium. One of them was on the coarser end of fine, and the other one was on the finer end of medium. Really, those DV50 numbers are very, very close to each other. And what this means is that when you see results for fine droplets in the following testing, you're looking at the best case scenario for these fine droplets, where they are the coarsest they could be and still be considered fine. Okay? And then you can see with our medium and our coarse droplet size treatments, we hit our targets perfectly. And by all means, we move from a smaller droplet size to a larger droplet size across our testing. So, what else did we do with our methods? Testing was conducted in Carrington and actually also in Oaks. I've neglected to update this slide properly. The row spacing was either 14 or 28 inches, depending on the study. Seeding rate was 90,000 viable seeds an acre. Fungicide spray volume was 15 gallons an acre. All these applications were made with a tractor-based sprayer equipped with a pulse width modulation system. And that pulse width modulation system allowed us to maintain a constant driving speed and a constant spray volume, irrespective of the output of that nozzle and pressure combination. The driving speed was either 6, 10, or 10.5 miles an hour, depending on the study. Number of experimental replicates was anywhere from 8 to 18, depending on the study. We used a large number of experimental replicates because white mold disease pressure tends to be spatially inconsistent. You can go from areas of low disease pressure to high disease pressure in short distances, and by having a large number of experimental replicates, we maximize the chances that every treatment is exposed to areas of high disease pressure and areas of low disease pressure approximately the same number of times. We assessed white mold by evaluating every plant individually in minimum half of the rows plot for the percent of the plant impacted by the disease. And then we harvested by clipping the plants at the base, windrowing them to let them dry down, and then passing the clipped plants through the combine. We did that rather than straight cut because if we were to straight cut, we would have introduced into our yield data a bias associated with any differences in lodging we saw across the footprint of the study. To eliminate lodging as a confounding variable, we straight cut. Finally, we applied supplemental irrigation overhead as needed to establish the disease pressure that was required to evaluate the fungicide treatments. For more detailed fungicide application methods, see this chart. In all the studies, we applied Topsin at 40 fluid ounces at the first application, and then Dura at 8 ounces in the second application. The nozzle and pressure combination that we utilized for those fine droplets differed by the study. The driving speed differed by the study, but was consistent within the study. And the application interval between applications differed by the study. The experimental replicates differed by the study, but varied from 8 to 18. We calibrated pulse width manually with the fungicide in the tank immediately before our application. We did this by collecting the output in these milk jugs. We ran the sprayer for precisely 10 seconds. If the output was a little bit too high or a little bit too low, we adjusted our pulse width until we got the output perfect, so that the spray volume was always 15.0 gallons an acre at the target driving speed for that study. Applications were made with this tractor-mounted sprayer. What you'll notice is that there's a driving path. That driving path was smoothed out with a strawberry cultivator to ensure that we did not have any big bumps, because we wanted to make sure that that boom did not sway. This video was taken in soybeans, and the picture was taken in soybeans, but the methods are exactly the same for the dry beans. What you'll notice when I play the video in a moment is that the sprayer operator turns on the boom right before he gets to that blue flag to the left of the tractor. Then he turns off the boom after that blue flag, and then there's a short distance before he hits the next flag. Well, that short distance was established specifically to be able to turn on and off the sprayer while maintaining your driving speed. That short distance between flags of different colors is not harvested, not assessed for disease. It exists specifically for turning on and off the sprayer without confounding the results of neighboring treatments. So with that, let's go ahead and watch the spraying application. So what did we learn? I'd like to start out with results for pinto beans seeded to wide rows. I have results for the individual studies presented, as well as bar graphs showing and a scatter plot showing the combined analysis across studies. In the results for the individual studies, I have shaded in a yellow light brown color the maximum yield obtained across treatments. Right away, what you'll notice is that we did not achieve maximum yield with fine, followed by fine droplets. Instead, we achieved maximum yield by applying with medium droplets first and then coarse droplets second. In one study, we optimized with medium followed by medium droplets, and in two studies, we optimized with medium followed by coarse. In this case, it's not exactly clear what parameters drove that response to optimizing the second application with the coarse droplet. But the differences were quite small across those two studies, and what you can say with confidence is that that first application needed to be with medium droplets and the second application either medium or coarse. Now, one thing you'll notice is that you do not see statistical separation among these droplet-sized treatments. What my experience is, or experience with the soybeans, was that because of the underlying variability in white mold disease pressure and the fact that we're looking at small treatments, what matters is the consistency of the results across studies. And with the soybeans, we needed to have results from 5 or 6 studies before we could achieve consistently statistical separation, but we would see the same results over and over. What I would tell you here is that these are the type of results that I'm accustomed to seeing on the soybeans, where we see very consistently that the fine followed by fine droplets was not optimal, and that we needed that first application to be at medium droplets and the second application either medium or coarse droplets. So those are pinto beans seeded to wide rows. What about pinto beans seeded to narrow rows? In this case, these are pinto beans seeded to narrow rows where the canopy was nearing closure at the first application. Look on the very top and you can see the canopy closure averaged 94% in all 3 of these studies at the first application. This means that looking at that canopy from above, only on average 6% of the ground was showing between the plants and between the rows, which means that canopy was nearly sealed up at that first application. In the second application, you can see we were at 97 to 99% canopy closure. Under those situations, we maximized yield with coarse droplets followed by coarse droplets, and now you can see that we achieved statistical separation because the differences were so consistent. But again, this is a situation where you had the canopy nearly closed at the first application and really virtually sealed up at that second application. In this situation, you have a dense canopy. You need those coarse droplets to get inside because the fine droplets don't have the velocity to penetrate. If you look at this in even greater detail, you look at the percent lodging across those 3 varieties that we tested, and you see the ND rhodeos were much more lodged than the other 2. And then if you look at the yield results, you look at just the yield gain from coarse versus the fine versus fine droplets. And what you can see is that the yield gain to applying with those coarse droplets at both applications was the highest where the lodging was the most severe. Now this makes perfect sense. As your dry beans tip over and they start to lean, suddenly the canopy becomes a lot denser. You have more trifoliates in a shorter height than if they were standing upright. And so again, what these results indicate is exactly the same as the canopy closure results. As that canopy becomes denser, you need to have a coarser droplet to get inside. So we've now seen what droplet size optimized fungicide performance in pinto beans seeded to narrow rows where the canopy was nearly closed at the first application. What about that situation where the canopy is still open at that first fungicide application? In these 4 studies, we seeded the pinto beans to either 14 or 15-inch rows, and the canopy was wide open at the first application. Canopy closure averaged between 52 and 80% at that first application, which means that there was between 48 and 20% of the ground showing between plants and the rows at that first application. If you look down on the top, from the top of that canopy, you saw a minimum 20% of the ground showing between the rows. At that first application, that canopy was still wide open. The second application, on the other hand, we were starting to approach canopy closure. What did we see in this case? Again, just like we've seen previously, in no situation did we optimize with fine followed by fine droplets. Instead, here we optimized with either fine droplets in the first application or medium droplets in the second, and then coarse droplets in all the studies in the second application. Now, statistical separation was minimal. We did see some separation versus the medium treatment, but otherwise statistical separation was not existent. But again, in my experience, what matters in these droplet size studies is the consistency of the response. With more testing, we'll achieve that statistical separation. What you can see here is that clearly fine followed by fine droplets was not optimal. Clearly, coarse droplets in that second application, as that canopy was nearing closure, was consistently optimal. The only decision you had to make was applying with fine or medium droplets in that first application. And that is always going to be contingent on how dense that canopy is. So let us summarize what we have learned by creating a decision-making chart. First, if your pinto beans are seeded to wide rows, 28 or 30 inches, what these research results suggest is that the first application should be made with medium droplets. And the second application should be made with either medium or coarse droplets, depending on how dense and how closed that canopy is. If your pinto beans are seeded to narrow rows and the canopy is near closure at the first fungicide application, you should apply your fungicide with coarse droplets at both applications. If the canopy, on the other hand, is open at that first fungicide application, you should apply that first application with either fine or medium droplets, depending on how dense that canopy is, followed by coarse droplets in the second application. So I have now provided droplet size recommendations for optimizing fungicide performance relative to canopy characteristics for improved white mold management in pinto beans. Let me stress, however, that these should be considered preliminary recommendations. In my long experience running these droplet size studies for improved disease management in field crops, we rarely achieved statistical separation with just 3 or 4 droplet size per canopy characteristic classification, i.e. the row spacing and the degree of canopy closure or degree of lodging or other variable. We need additional studies to achieve that statistical separation, and having those additional studies gives us additional confidence, because as we see the same response over and over and over again, it gives us much greater confidence. We'll be looking to develop these additional data as we go forward. In the meantime, have confidence that the results that we have seen within these different canopy characteristic classifications have been consistent, and by all means, we have never optimized fungicide performance against white mold in pinto beans by spraying with fine droplets at all applications. The fine droplets were only optimal when that application was made to a canopy that was wide open and that had virtually no density to it. The second point I'd like to stress is that these are results obtained from testing with TJET nozzles. Now, we use TJET extended range flat fan nozzles, and I don't think that that nozzle type is that important. In my experience working with these different nozzles produced by the same manufacturer, what matters is the nozzle manufacturer. Within TJET, I would expect similar results across all their nozzle types. However, as you move to a different nozzle manufacturer, the droplet size optimum can change. In our testing conducted in soybeans for white mold and on other crops for various foliar diseases, we have seen that the droplet size optimum for Wilger versus TJET is often different. With the Wilger, the optimum droplet size for Wilger often one step higher than TJET. So if a medium is optimum for TJET, then a coarse is optimal for Wilger. Now, the relative performance of different droplet sizes is always consistent. So if a coarse droplet is better in TJET than a medium, well, then a very coarse droplet is better for Wilger than a coarse for Wilger. So these droplet size optimums that I have outlined here are for TJET nozzles, and I must stress that. We must conduct testing with other nozzle manufacturers to identify what the optimum is for this crop with that nozzle manufacturer. Finally, I'd like to thank my staff, Aaron Faust, Swan Collis, Jesse Hafner, Gabby Henson, and our seasonal student workers, and also the staff in Oaks, Heidi and Spencer Esslinger, Kelly Cooper, Leonard Bestman. These individuals have all worked very hard and worked long hours to ensure the successful execution of these studies. I'd also like to give very sincere thanks to the funding agencies that made this research possible. The North Harvest Bean Growers Association, these are your checkoff dollars, and the North Dakota Crop Protection Harmonization Registration Board, administered by the North Dakota Department of Agriculture, and the USDA Specialty Crop Block Grant Program, again administered by the North Dakota Department of Agriculture. These funding sources provided the funds to pay for the staff to do this work, and also provided the funds to purchase the supplies and make the equipment repairs necessary to conduct this work. I'd also like to give very sincere thanks to the private companies that do contract fungicide testing with us, because it is the funds from that testing that has allowed us to invest in the equipment needed to do this work. Our plot combine was purchased with those funds. That tractor and that sprayer that you saw in the video was purchased with these funds, and other critical equipment that we use to execute these studies was purchased with those funds. Without that funding, we could not conduct this research. Finally, I would like to give my very sincere thanks to Bolingbird Seeds, Green Valley Bean, and Kelly Bean Company, who have donated the dry bean seed that we utilize to execute this and other dry bean white mold research. Sincere thanks for your time, and I hope that these results are useful in informing your operation and improving your operations. Thank you very much.